So what are the main things we have learned in these days? You tell me. So what are the take-home messages that we, hopefully many? So
In the transversizing model, we have a phase transition.
okay. So the first thing that we have understood is that in the quantum or transverse field Ising model, there is a quantum phase transition, right? So what is a quantum phase transition as opposed to a normal phase transition?
At zero temperature.
What?
It is at zero temperature.
So quantum phase transition means it is at zero temperature, so it's driven by what?
Quantum fluctuation.
The quantum fluctuations, and so means that it's not the temperature that drives it, right? It's some other parameter in the Hamiltonian. So we have some Hamiltonian depends on some parameter, and so the quantum critical point is some value of this parameter that we call quantum critical point, and for this model is how much?
1.
Is 1. Okay. So we have two phases. Okay. So first of all, how do we locate this? Why? What is our notion of being a quantum critical point?
You have this self-dual method.
Yeah, but why that works? What do we look for when we do self-duality? Why by self-duality we can get GC equal 1? What is that we impose?
Well, when the gap goes.
Yeah, okay. So a quantum critical point for us means that the gap between the ground state and the first excited state at G equal GC is 0, and we know this can only happen unless it's a level crossing in the thermodynamic limit, okay? And so we know that some, so this is not one point, it's the summary. Okay. So we have this feeling that because something important is happening here, namely the gap is going to 0, then these two regions have some very different qualitative behavior. And we found it. So what is the difference between, so what happens here, G small and G large, at least in this model, that is the prototypical model for quantum phase transitions. So what is this phase? First of all, how we call it?
Paramagnetic.
Yeah, paramagnetic. This is a paramagnet, right? So, let's first do the paramagnet. It's easy. So, what do we have in this region? What are the characteristics?
No ground state degeneracy. Unique ground state.
Unique ground state. And which already tells us something. If the ground state is unique, means that something cannot happen. So what is it cannot happen? So this model has a symmetry, right? As a Z2 symmetry. What does it mean? That if I change all the spins by flipping all of them, the energy doesn't change. Or in other words, Hg commutes with this operator that is flip all spins. Right? So there is a symmetry. So if there is a unique ground state, this means that also the ground state has the same symmetry. Do you agree with that? Because if there were two ground states, then this operator must commutes to the Hamiltonian, so it must operate in that subspace. So it makes you move in that subspace. If you have two states, then this must happen, which means that psi1 is not, doesn't go into itself. Or at least this can happen. But if there is a unique ground state, it must have the same symmetry of the Hamiltonian. So there is no broken symmetry. And the consequences of these things is that the correlation functions decay exponentially. And psi is equal to the gap to the -1. Okay? So you see that we have a quantum phase transition because we have a symmetry that is broken in different ways, meaning on this side is not broken, and on this side is broken. And because Z2 is a very simple group, it's broken in the only way it can be broken, right? In something that has no left symmetry anymore. But when you have bigger groups, you might break it to a subgroup of it, right? So you can still have some residual symmetry. So in this simpler case, you just have no other symmetry in the ground state here. So here we have the generated ground state, broken symmetry, which means this thing that I wrote here, that the two states, psi1 and psi2, are related one to the other through the symmetry. What else? Then we have, because there is a broken symmetry, there is spontaneous magnetization. Spontaneous magnetization. Right? So what does it mean is that the expectation value in the ground state of sigma z is different from 0. So it's some function of g. And finally, the connected correlation functions, so let me put it here, also go in the symmetric state, otherwise it's not the connected ones, it's the disconnected ones. We know what all this means, also are different from 0. So we have two qualitatively very different behaviors. And so we see that our ground state manifold as a function of g, so for every value of g, we have a ground state of this model, splits in two parts. And that are the two phases. Inside each phase, the system has a gap. And the energy is smooth as a function of g. Here something weird happens, right? Here we have some non-analyticity of the energy. But how do we distinguish the two phases is because one has the Z2 symmetry and the other one breaks the Z2 symmetry. So the picture right now seems that if we have a generic Hamiltonian in terms of many parameters, and we look at all the possible ground states of this Hamiltonian, well, if this Hamiltonian has some complicated symmetry, then this manifold could split in different regions that are all marked by different ways of breaking the symmetry. So in this case, there is only one way of breaking Z2, but if you have a larger group, then you can not break it to a subgroup, to a smaller subgroup, and so on and so forth. And an interesting question would be, is this picture exhaustive of all the possible states of the matter, meaning ground states of reasonable Hamiltonians? Why do I have to say of reasonable Hamiltonians? Because for every state in Hilbert space, there is a Hamiltonian such that that is that ground state, right? Yeah. Is this a profound or trivial statement?
Sorry.
This statement that for every state in the Hilbert space, there is some Hamiltonian such that that state is its ground state. Is this statement a profound or trivial statement? Why it's trivial? Yeah.
Identity minus projectile.
Yeah.
Yeah.
Yeah. So you can easily write down, you just write your Hamiltonian like minus some constant, doesn't matter, the projector onto this state plus some positive numbers orthogonal projectors to this. Okay? So you see, it seems that, so because every state is the ground state of some Hamiltonian, this picture does not seem reasonable, right? Because there could be, family of states that are connected no matter the symmetry. The point is that we cannot use any Hamiltonian that we want, right? Here, when you write this, you have no idea whether this guy is the sum of local operators. Right? There is no notion of locality here. This is a projector onto the Hilbert space. How do we know that this guy has the form? Remember, our Hamiltonian must have this form. If it must be the sum over local operators, otherwise the thermodynamic limit doesn't make sense. So in general, we, saying the states that we are interested in are ground states of local Hamiltonians, this is a big restriction on the Hilbert space. So that some more structure could emerge. And in fact, people expected for a very long time that this means that all the states can be classified by symmetry. Not all the states in the Hilbert space, but all the reasonable states, meaning the ground states of local Hamiltonians. Okay. So we know that if this is the case, if symmetry is all that counts, then when we do not break symmetry, we must have this situation. And that when we break symmetry, we must have some long-range order. So if we want to find some other kind of order, we should find a way to have a degeneracy without symmetry breaking. So this would be a new situation that is not like symmetry breaking. Because every time, so far we see that the degeneracy is due to symmetry breaking, and therefore long-range order and all the rest. Okay? So this is something that we have as a goal in mind. So we have located this critical point in two ways. The first way is perturbation theory, okay, which you have seen that the gap goes like 1 minus g. The second way is self-duality. So because the model is self-dual, if there is a gap that vanishes at some value g, then it must also vanish at the value g to the minus 1, so g must be 1. But this one model is also exactly solvable. How do we solve it exactly? So today in the tutorial you will do all the details. I don't know if I have to say something at all, but actually, so Dennis wants me not to say anything, right? You will do it. It's a free country. Yeah, okay, yeah, so.
Next question.
Sure.
We get the critical G from self-duality. Is there any other conclusion to draw from the property? Like we have shown pretty duality, but anything that is getting G?
Well, we have mapped the spectrum of what we've done is that we've seen that G E of G is equal 1 over G, sorry, is equal E G minus 1. Okay, so it's the whole spectrum that has this property. So this means that you can map these energies into these energies in this way. A consequence of this, there is another important consequence, is that, so far, because we are really interested in the notion of a quantum phase, so what is when only quantum fluctuations are present, so we are at zero temperature. So for us, the states of interest are ground states. But of course, in general, we are interested in all equilibrium states, so also the Gibbs state. And so there is also temperature. So one consequence of this is that also the properties of low temperature map into the properties of high temperature. And if you want to see details about this, you can see this very old Review of Modern Physics from 1979 by Kogut. And there is a thorough explanation of this. So this is a very, very good read. But showing you this would take us a couple of hours. I cannot do it right now. But yeah, you can map low temperature and high temperature in the two models. Remember, though, that the degrees of freedom in the two models are not the same, right? Because there is a non-local transformation between them.
But eventually, like dual model is exactly the Ising.
It is the Ising model, but not in the same degrees of freedom. It is again the Ising model in non-local degrees of freedom. So I'm not saying that if the system breaks the symmetry for large G, it's also breaking the system for small g. It means that it's breaking the symmetry for small g in the other degrees of freedom. Okay, so this is a subtlety that is worth remarking. Okay, so now we start. Okay, so I will leave to Dennis altogether the topic of diagonalizing the quantumizing model. And so there is another model that is diagonalized exactly in the same way. That is the XY model that has this form. So you have a minus, you have 1 plus gamma over 2, sigma x I plus 1, plus 1 minus gamma over 2, sigma y I plus 1, plus lambda, sigma zi. So this is diagonalized exactly in the same way. So if you, after the tutorial of today, you can actually apply the very same method to diagonalize also this model. Of course, the final result is slightly different because this, there are more terms, and basically this has a richer phase diagram. You see, because now it depends not just on G, but on two parameters that are gamma and lambda. Also notice that for gamma equal 1, this term goes to 0, and you are in the quantumizing model. And so this one is called the XY model. The phase diagram, meaning where delta E goes to 0, is the following. So if you here have gamma, and here you have lambda, and there are now not a critical point, but there are critical lines because we're in 2D. So at lambda equal +1, at lambda equal -1, and all gamma equals 0. These are critical lines. As I said, gamma equal 1 is the Ising model. And you see that we find again the critical point at lambda equal 1. Ha! Okay. Okay. Very good. Okay. So how do we find this phase diagram? Again, by solving for the model, finding the gap as a function of gamma and lambda, and checking where it goes to 0. The interesting thing of the analytic solution is that this solution only exists for n going to infinity. So there is no solution to the question delta E going to 0 unless n goes to infinity. So you really see why it can only happen in the thermodynamic link. But now we want to improve our criterion for what is a quantum phase transition. So far, I told you the first day it's when the system becomes gapless, but this is not good enough. And the reason why it's not good enough is because so for two reasons. One reason is due to Paul Anderson, who started to develop this idea that he sketched that thought, a quantum phase must be a domain of adiabaticity for the ground state. What does it mean? It means that somehow if I am within a phase, so I have my ground state for some value of lambda 1, I should be able to change my Hamiltonian very slowly so that I'm always in the ground state and go to lambda 2 without, being very reasonable to be in the ground state of say lambda 2. In the ground, sorry. I have my h of lambda, I change my lambda such that I go from, because what I can do in the lab is to change the parameters of the Hamiltonian. So I change the parameters of the Hamiltonian slowly so that I am in h lambda 2. And if I can do it adiabatically, then if I start from the ground state of h lambda 1, I have a good probability of being at the end of the process in the ground state of h lambda 2, which is psi lambda 2.
In the argument, why the adiabatic change is important? I mean, if we solve h lambda 1 and if we solve h lambda 2, we have a ground state, right?
Yeah. So the fact is that, if I don't have in mind this adiabatic continuation, then there is no reason why I should not be able to prepare also this. Right? So, I also have h of lambda 3. I don't do it adiabatically. I prepare h lambda 3, then I freeze the system, I go in the ground state. And I have completely skipped the quantum phase transition. The idea of Anderson is that if I am in the same phase, I can do it adiabatically, so changing slowly. But if there is, if the two states are separated by a phase transition, then I cannot do it, right? I hit a wall. Meaning, if I try to do it, when I arrive to h lambda 3, I am not in the ground state. The adiabatic criterion fails. Now, have you done the adiabatic theorem in quantum mechanics? So so let me state it because I said it maybe too quickly. The adiabatic theorem. So this is a very fundamental thing in quantum mechanics. So if you try to solve the Schrödinger equation, so there are approximation methods, right? So one very interesting, so if I change my Hamiltonian as a function of time, the solution of my Schrödinger equation is the time order product of e to the minus this thing, right? So as you know, this is a very beautiful thing to write, but how you exponentiate this, right? This is very hard because in order to do the exponential of an operator, you must know the exact eigenstates, which usually you don't, especially for a many-body problem. So this is a formal solution. However, one of the approximation methods is the adiabatic approximation and says that if this t is very large, meaning if I'm moving very slowly, and then you have to ask me what is the time, what is the typical time, what does it mean? Okay, we'll see. If you move slowly enough, then if my initial state is an eigenstate of the Hamiltonian, my time evolved state at the time t will be in the corresponding eigenstate of the Hamiltonian at the time t. So if now I do this for starting from the ground state, and my lambda is the parameter that changes with time, so it's a lambda of t. If I move slowly enough, if I start from the ground state of psi lambda 1, of h lambda 1, I will end up in the ground state of h lambda 2. If I move slowly enough, right? So what is slowly enough? So this time should go like what to be slow enough? You know? So if you do the adiabatic theorem, so typically people say, oh, this has to go in this way. This, you prove the theorem, and you find something order 1, some constant, over the gap square, the gap between, in the case of the ground state and the first excited state. If you are in any other eigenstate, is whatever energy, smaller energy there is between this eigenstate and the others above or below. All right, so you see that here, this thing is doomed to fail because it's becoming gapless. Okay, so that's why Anderson is saying, oh, if I take this other definition that has some, it's like some operational thing that I'm doing, but it should give us a similar result. So, but why this is better? This is better because when you really do the adiabatic theorem, you will see that up here, you don't have just some constant. So you have some constant order 1 when you don't care about n. What you really find is something that goes a bit like this. It's like the sum over the excited states of the tunneling between the ground state and the excited state of h dot. So you see, it depends on how fast the Hamiltonian varies and how well the Hamiltonian makes you tunnel, this derivative, not the Hamiltonian, the derivative of the Hamiltonian makes you tunnel between the states. And when this is a many-body system, this is a many-body operator, and then you have this sum, then this can be a big number. Or it can be a small number. It can be many things. It has a scaling with n. So you see, this leaves the door open to the fact that maybe the system is becoming gapless, but this Hamiltonian is not able to make me tunnel between these two. There is some topological obstruction. It does not connect them. Then I don't care that the system becomes gapless. So maybe I can still move adiabatically even if the system becomes gapless. In fact, we have situations like this. We have some disordered systems that are gapless, and you expect that there is conductivity there because there is no gap, so that charge carriers can move, but there is a so-called mobility gap, some effective gap, which just means that you are giving up with this gap condition because actually there is no gap. So the bottom line, the system can be in the same phase even if you have some gapless excitations. So we need to update our criterion, taking seriously this adiabatic continuation. And if we do that, and we are going to do that right now, we discover something beautiful from 3 points of view separate come together. One point of view is this: okay, we need to take into account that there are condensed matter systems in which there are obstructions in tunneling, so that the gap is not the only thing that counts.
Is that the time scale of the adiabatic change? Like, if t greater than that time scale means it is slow process?
Yeah. So t should be much. T should be much greater than some characteristic time that goes like this. Thanks. So the three points of view that come together are the following. So the first one is that, okay, we need a better criterion because the gap is not all that counts. The second is a mathematical structure. We will see that looking for this type of stuff will allow us to see that the ground state manifold as a metric, like in general relativity. It has a Riemannian metric tensor in it. And the third is an operational point of view in which we will understand that being in the same phase means this. So two states, two ground states of local Hamiltonians are in the same phase if they are similar qualitatively. But so far, we have said that many times, and we said, qualitatively, in this case, for instance, means that they break the symmetry. They do not break the symmetry. But now we are not looking for some quality that they have in common. We want a general criterion. What does it mean for two states to be similar? Okay, so we start this investigation exactly from this point of view. What does it mean for two quantum states to be similar? Operational, from the operational point of view. Well, in some sense, the wave function is not really something physical, right? What is physical in the Hilbert space? You never see the wave function. What is the most, the closest thing to something physical that there is in the Hilbert space? Is the probability distribution that comes from psi lambda, right? So this one is some object that is mathematical, but this starts to be something physical, right? It's some probability distribution. And of course, we also have classical probability distributions, P1. So we could say that if we answer this question, how two classical probability distributions are similar, then we can answer this question, how two states are similar. However, there is a big difference. So this is, although this is a probability distribution, it's not really like this. And we will see exactly why. Okay? So let me start from the classical case. So imagine that we have two probability distributions. And let's start with something very simple. We have a coin. Okay? We have two coins. And we want to compare them. We want to see if they are like the same coin or not. So the first coin has a probability P1 to give heads, and the probability 1 minus P1 to give tails. And the second coin gives me P2 and 1 minus P2. Okay. And by the way, the variance of a probability distribution like this will be the square root of P1 minus P over the number of trials. And is the number of times that I toss the coin. And I want to find a notion of what is the distance between P1 and P2. Okay? So imagine that P1 and P2 are close, because we want to find something that is a distance that then I can integrate, right? So when I have two distant far apart probability distributions, I compute this distance by summing over all the small distances between similar probability distributions. So they have some variance that is very similar. Well, you know that if P1 plus P2 is smaller than 2 delta P, so if these two averages are smaller than the sum of the two variances, I cannot distinguish the probability distributions. Usually, so this is a too simple example, but in the Gaussian case, you have something like this. You know, if they're wide enough and they overlap, you know, there is too much overlap. If this distance is smaller than the sum of these two, then you don't know if they are the same or not. You cannot clearly distinguish them. So we could take this as a working definition for our elementary distance and say that the distance between two probability distributions, P1 and P2, is equal to, I want to put this guy 1 over square root of n for the sake of normalization, and then say it's equal to the number of intermediate distinguishable distributions. So what I'm saying is the following. Imagine that I have this distribution that is P1 and this distribution that is P2. And what I'm saying is that, okay, so this is the first, according to this criterion, the first distinguishable probability distribution, then this is the second, the third, and I count them. And this is the distance. So if I do this, so my definition is 1 over square root of n, the integral between P1 and P2, dp of 2 square root of p 1 minus p. Within this.
What if, like, probability distribution of like P1 and P2 are very different? Like, what kind of distribution should I put to count the number of...
So you should put the 1 such that saturates this, right? Such that the distance between two D's is exactly equal to the sum of these two, which is what I did here. See, the dp is weighed by this guy. That is the variance, the sum of the two variances. If you do this integral, you find the arc cosine of p1 1/2, p2 1/2. Let me call qi 1 minus pi plus q1 1/2, q2 1/2. This immediately generalizes to a more complicated coin, meaning a probability distributions with not 2 outcomes, but a number r of outcomes. So immediately, this distance between the first probability distribution and the second probability distribution can be defined as cosine to the minus arc cosine of the sum over I p1 I 1/2 p I2 1/2. Okay.
Can you repeat how you get the integral over there, like dp over 2 or the p1 minus?
Because you see, this guy is, apart from the square root of n, that then I'm taking care here, is the variance between two close probability distributions such that they are distinguishable.
But why can we get rid of the square root of n? Like, why delta p, and it looks slightly different, but
because you see, so we want this because so you're asking me why you want the square root of n?
yeah.
It is to take care of the square root of n that is there.
Then why 1 over? I mean, it,
So
it looks like it should be like. So you are integrating over inverse of delta p, but why do we? I thought that we have to, like there's a length divide by. I mean, I cannot see why there is 1 over square root of n, because I thought that it should be square root of n over p times 1 minus p. And if there, yeah. And if we just put the 1 over square root of n in front of the number of intermediate distinguishable distribution, I thought that it should be not the 1 over square root of n, but the square root of n times p1 to the p2. And the difference of p.
Yeah. Okay. So it's this way. Our dp delta p is the square root of p y. So we are concerned with this, okay? And this goes like, so you have this relation. So we want to count how many of these guys there are, you know, by splitting it in intervals like this. Okay? So in principle, we could just count like this, right? We could just do integrated this guy. We could define it in this way. However, I want to get rid of this guy. So I don't want this object to depend on square root of n, so I'm getting rid of it.
The basic idea is still the like integrator of one of the top key, but by convenience choice, like we just take.
Yes, I want to normalize because the variance depends on n, right? Because the more triads you have, the smaller becomes the variance. Okay, so this is the distance between two classical probability distributions. But now I'm asking, okay, yeah, let's go back to the quantum states. How we get probability distributions from a quantum state? So what we do is that we have observables. We have observables. So we have Hermitian operators that have a spectral resolution. So they have some eigenvalues. And these are the eigenstates of A. And the way in quantum mechanics you get probabilities is the probability of having the outcome AI. So let me call this the probability I when I measure A, which is given by the Born rule, right? If you are in the state psi, so you're in the state psi, psi is your state, is this. Okay? So this is ordinary quantum mechanics. This is how you get probabilities. So once you do this, this is a classical probability distribution. And now if you have two states, so this is psi1, if you have two states, then you will have the probability distribution when you measure A that comes from the first state, and the probability distribution when you measure A that comes from the second state, and you can compute this distance. And to compute this distance, now you can use this formula. Okay, so this is how, now we can measure the distance between two states seen as probability distributions by looking at the probability of the outcomes of experiments. It's an operational thing. However, look, this is the probability distribution when we measure A. So this is the fundamental distinction between classical mechanics and quantum mechanics. A classical probability distribution is the probability distribution of a configuration, and it's the same for all the observables that you have. If you have an observable that is a function of your phase space, the probability distribution for that configuration is the same no matter what function you are measuring. But in quantum mechanics, well, no. In fact, imagine I get another observable, B. So I have two possibilities. If B commutes with A, then they have a common basis of eigenvectors. What does it mean? What it really means is that B can be written in this way, where now this is the same basis than before. It's the one that I wrote like this. So you see that if I extract the probability distribution of getting the outcome BI when I measure the state, some state, but when I measure B, okay. By the same token of this, you see it's the same, because this is again the projection onto the eigenstate. It's the same that I had before. So when observable commutes, their expectation values refer to the same probability distribution onto the configuration of your space. Right? Because it's the same probability distribution on the same configurations. But when they do not commute, so we say, oh, they're incompatible measurements, what it really means that now these are completely different eigenstates. So this is a completely different probability distribution. Not only is it numerically different probability distribution, it's a probability distribution onto a different space of configurations. So they're really incompatible, really. It's like when you measure A, you are measuring some reality, and when you measure B, you're measuring some other reality. So all quantum mechanics derives from this. The moment you write it as a linear algebra with operators, now they cannot commute, and what it means that they give you different probability distributions. So now we are in trouble, because you see, we have our distance between psi1 and psi2 depends on what I measure. I have some distance when I measure A, some other distance when I measure B, and so on. Well, so I could say that the distance between two states altogether is the sup over all the possible measurements of dA. So I can take this operational point of view in which, okay, I have two states that look very similar just because I'm measuring an observable that does not distinguish them very well. But if I take the right observable, I can distinguish them more, and I call the distance the biggest of this distance. It's like what you do when you have two sets in a metric space, and you don't take the distance in this way, you take the distance in this way. This is the distance between South America and Africa, right? This one, not this. Okay, so this is our distance. And now we need to, so the seemingly ugly thing is that this seems very formal, because the space of all linear Hermitian operators onto a Hilbert space is something humongous. So how do I do this sup, right? It seems a very daunting, very difficult task. And in general it is, so every time you see definitions that contain some sup on the Hilbert space, and that's it, you must be very skeptical how useful they are, because usually this is a complex task. However, in this case, it's simple. Because you see, so let me show you why. So if I plug my definition in here, what I have is the following thing, is that the distance when I measure A between psi1 and psi2, so I'm using that definition, okay? So it is cosine to the -1 of the sum over I of my probabilities, right? And the first one is phi A psi 1 modulus square, but then I have the square root there, right? Times, again, I can write it like this. Yeah. No, I just write it the way it is. Psi 2. And then I want to make the soup of this, the soup over all the A. So I need to choose the A such that its eigenstates are, or one of their eigenstates, as the maximum of these overlaps. So you see that the best possible observable that I have is an observable that contains between its eigenstates psi 1. Because the best I can do to maximize this overlap is to put psi 1 here. No, I saturated the bound. In other words, if I take an observable that has this form, A1, psi 1, psi 1, plus other terms that are orthogonal, this saturates this bound. And what do I get? Well, all the terms but the first one are orthogonal, right? So send everything to 0. And the first one gives me 1. Right? So I just get cosine to the minus 1, psi 1, psi 2. Oh. So now we know why this angle, because this is the angle between two states, is the distance between two quantum states. It's the distance intended as statistical distance in operational terms when I make measurements. And this is, yeah.
Why do you want to maximize the overlap there? Like, wouldn't you want to?
So you want to find the A such that this thing has the maximum value.
Yeah.
So you cannot have a max. You know, the best you can do is to have 1.
But cosine inverse would be most when this is smaller.
This. So I want this angle. Sorry, you're right. Okay. Yes. So I want to take the soup of the arc cosine. So this is such. So you're asking me why the most discriminating. You know why I reach the. You're right. Okay. So I guess this is not so immediate. However, well, there is at least one easy way to see that, is that for sure the most discriminating thing that I can do is to project my state psi 2 onto psi 1. I mean, to check directly whether psi 2 is psi 1 or not. So this is what I'm doing. My projective measurement is a projective measurement of psi 1. Okay. And, all right. So this guy is called fidelity. Fidelity. It's the overlap between two quantum states. And, okay, so this is the distance between two any states. Now we want to find a notion of the distance when two states are close. Okay, some differential. So this happens when the fidelity is close to 1. Then this can be written in this way. So this differential distance is called DFS by the names of the people Fubini and Studi metric. It's called Fubini study metric or distance. Okay, why I didn't do something simpler, like taking the, because I'm measuring a distance between states. And we already know that the Hilbert space is a normed space, right? There is a norm. So in a norm, every time you have a norm, there is a distance associated to it, and I could do this. I could say, oh, this is the distance between psi1 and psi2. I could have done this. So there are two answers. The first answer is that if I do this, this is a mathematical formula, and there is no notion why we are doing that. Here we are really trying to understand the distance in terms of how we can statistically discriminate to quantum states. But there is another reason. So if I use this, so why this is wrong? Why it's profoundly wrong. It's another important property of quantum states. Are quantum states vectors in the Hilbert space?
That's it. If you have phases.
They're rays, right? So if this means that this state and this state are the same quantum state. But as vectors in the Hilbert space, they are different. But you see, I'm not measuring the distance between vectors in the Hilbert space, but between quantum states. So this means that if I could, I don't really have this. I have this guy, maybe. And now this is not invariant by phi1 and phi2. So you see, it's not. The thing is that I am making them interfere. But when I measure two quantum states independently to see if they're the same or not, I'm not making them interfere. Here, it's like physically I'm making them interfere. So what I could do is to take the inf of this among all the phi1s and phi2, and then it will not depend on phi1 and phi2. So mathematically now it becomes sound. And operationally we don't know what the heck it means. Now I really don't know how to make this inf. However, there is a beautiful theorem, and guess what? Theorem, this guy is equal to this. So if I started all the way, from this, I would get the same result. So the right mathematical definition is also the operational one. Okay. This is the distance between pure states. There is a related distance between mixed states that is called trace distance. It's the max over all the possible operators of the expectation value of A in rho minus the expectation value of A in sigma. Is by definition the distance between the state rho, mixed state rho, and the mixed state sigma. Homework proved that is equal to 1/2 the distance between operators in one norm, in Schatten one norm. Homework. Oh man, it's late. And it's related to this guy, to the fidelity in this way that the square of the trace norm is equal to 1 minus f squared. All right. Now, what I would like to do, but I don't have the time to do right now, so we see it Monday, but let me tell you what it is. Oh. I don't need to. It's the following thing. So we have this differential distance between two states that we have defined like 2, 1 minus f. Okay? And now I want to apply this thing to the case of our ground states of Hamiltonians. So I remind you what we have is some Hamiltonian h of lambda, where lambda is a set of parameters. And for every lambda in this manifold, we have the ground state of this Hamiltonian, which is psi 0 of lambda. And I want to compute this guy for two states that are close. The overlap between two, so this is the overlap between two states that are close.
We can consider this on Monday.
Yeah. Yeah. So let me finish this sentence, okay? I will not do the calculation. So, you know, I have some curve, I have two states that are close. I want to compute the overlap of that. What I will show you is that when you do this by computing the overlap between this guy and psi of lambda plus some little thing, this overlap, and you put it in here, you will get something that has this form, where this is a metric tensor and becomes like a general relativity. Well, not really general relativity. The only reason is that this is a Riemannian, it will be a Riemannian tensor, not a pseudo-Riemannian tensor. So it's just about the space, not time. Okay, so we continue Monday.